had a problem with my computer. Welcome everybody. We've done a previous webinar on CPeTIT, but because now we have a version 2 of it, I've had a few requests where people would like to have another set of worked examples, but now using version 2. So that's what this webinar is about. And just a reminder again that much of what we talk about is in the CPT guide, which you can download either from the Gregg website or mine or from Geologist Mickey's website, and it's also available in other places. And of course, it also a reminder about the webinars that this is a series, and this is actually number 15. So there's quite a resource there if you want to go over some of the information in detail. So what we're going to do today is we're going to talk about this software program. It's pronounced CPeTIT. I mean, originally when it got started, we thought about calling it CPT-IT, and then we put the E in there to spell the word petite, which is French for small, so it's sort of a play on words of a small CPT program. So it's pronounced CPeTIT. And we're on to version 2 now, partly because of Microsoft changing their various systems, and which required a rewrite a little bit. So I'm going to now get out of the slides, and so I've got the program here, and then I'll just open it up so you see it says it's CPeTIT number 2, and this is what the program looks like. It has a very similar look and feel to version 1, so those of you that have used version 1 should find it pretty easy to adapt over to the version 2. It's got the same format. You've got a file management to the left, you've got plots along the bottom, and then you've got the data above. And typically I like to look at the plots a little larger, so you can drag that screen up to make the plots a little larger. I'll still keep one row of data because we might want to actually look at some of the data. And you've got the various buttons up at the top. And typically the first thing you want to do is you want to set the project information. So there's a tab called Project and Project Parameters. So you would give the title of the project. We'll call this example. And you set the units. We're going to use SI units today, but you could go to imperial units if you want to. And you've got a choice of plotting the data either versus depth or elevation. We're going to plot it versus depth. Most people tend to, but you do have the option of plotting it with elevation. And so if you know the starting elevation, you can show everything relative to that. And then company information. If the first time you use the program, you can import your own logo, load it in, and then put in your own information, and then save it as default, so that all the plots will have your logo and whatever information you wanted there associated with the name and address. Of course, it comes with Geologist Mickey's logo and name, but you don't have to use that. You can load in your own. And then there are some display settings, which we'll come back to later because we'll change some of these. But for now, we'll go with SI. And when you want to load the data in, you typically would click the CPT data button and then import a file. And then you've got options of text, exile, and then GEF, which is a manufacturer's format, or you can an empty file, which you could actually type data in, or you could import a previous CPeTIT file or even a slick file for the liquefaction program. But we're going to import a text file. A lot of CPT data is often in text format. And then, of course, it basically then says, okay, now go and find it, and I've already opened it. So here it is, CPT example, and it's the .cor files. There's 3 of them here. If I were to click on one of them, it gets displayed, and this is Gregg data, so it's got 2 lines of header information and then columns of numbers. And if in Gregg's format, if you scroll right to the bottom of the file, it tells you what the units are. So the first one's depth in meters, and then it's tip in tons per square foot, friction in tons per square foot, and pore pressure in PSI. And so because I'd opted to use SI units, and because it's a Gregg file, it's a COR, so the program recognizes it's a Gregg file, and so it's filled out all this information. It knows that the decimal delimiter is a full stop, and then the data is separated by comma. The data starts on line 3, and then the depth is column 1, tip is column 2, friction is column 3, pore pressure is column 4. And you do have an option for other data. So if there was other data like inclination, then that could be imported as well. And then, of course, it's already filled out the information. The depth is in meters, and it's going to convert the tip from TSF to megapascals, the sleeve from TSF to kilopascals, and the pore pressure from PSI to kilopascals. Now, if I clicked import, it would take in just this one, but if you've got multiple data like we have, there's just 3 here, if I left click and scroll over all 3 of them, then I can import all 3 of them. And they come straight into the program, and it automatically shows me the first one. So here's the first, second, and third one. And in the bottom left-hand corner is a little thumbnail sketch of the soil profile there. If I've got lots of CPTs, sometimes I'll remove that. I'll take out the detailed view to allow me to see more, and I'll even remove the thumbnail so I could list all of the CPTs there if I had more than 10 and it was filling up the column. And the program, of course, doesn't know what scales you want to use, so it reads in, and all the plots are based on maximum and minimum values. So usually the first thing you want to do is you want to try and fix the scales to a convenient set of values that will suit your project. And here, all of these CPTs were basically to 30 meters. And so if I just click on the depth axis, any one of them, I get a dialog box, and I can adjust it to go from 0 to 30 meters and say apply that to all of the plots in this CPT, and now they're all plotted 0 to 30. And I do that with each of the scales. Here I'm going to go out to 30 megapascals and so on. You do that with all the scales, and there's a variety of plots. So what I'm going to do is I'm going to actually load in the project file where all these scales have been fixed. But before I do that, I'll also illustrate how you would load in additional information. So there were dissipation tests here. So if I go up to the calculate button, there's a dissipation interpretation button. If I open that, it shows me the dissipation test module, and I can load in a file, and it's in Excel format for the Gregg data. And so I actually have to go in search of this data because I had not previously been there, so bear with me while I search for it. So it's in the Gregg webinars, and it's in the example file, COR, and it's in the pore pressure data. So here it is, and I happen to be in CPT number 3 here. Now there's quite a few, so CPT 3 is at the end here, so just scroll over, here's CPT 3, and it's in Excel format, and so it asks for the information, says the data in Gregg, it starts on line 2, and the depth for this one, I've chosen the one at 10.83, and the time is column 14, and the pore pressure is column 15, and it's already in KP, no, it's, I actually have to convert it from PSI over to KPA, and you import it, and now you'll see it. So there it is there. So that's how you do it, and so what I'm going to do is I'm going to now switch over to one where I've already done this, and it just saves a little bit of time. So I'm going to open a previous project file. It's asking me, do I want to save this? And no, I don't. This was just to illustrate how you load the data in. And so here's the file. So it's the same project. Now it's all been loaded in. And now when you look at the plots, you'll see all the plots are, the scales have been fixed to scales that are suitable for this project. And that will vary from project to project. Now, rather than do this on every project, because it's quite a lot of plots and it's quite a lot to fix, is once you've fixed one set of CPTs on like this page of plots, if you just double click on any one of the boxes, you can then say apply these scales to all of the CPTs in this project. So if I had like 50 CPTs in this project, I've only adjusted one set of scales, but now I fix them to all of them. And of course, I do that on all the plots. And then once you get a set of scales that are likely to be close to what you use a lot, there is a button up here called Plot Scales, and this allows you to save these scales as your default. So if I click here, it will save these scales I've used to become my default. And then if I click Load Default, it just will automatically convert all of the CPTs in this project file to those default set of scales. So I use that feature quite a lot. And then often maybe it's just the depth that I have to modify a little bit. So I pretty well got most of the scales fixed the way I like, and so when I load in a project, I just go to Plot Scales and then load the default, and then I'm pretty well there. This is a really important step. I see a lot of people will send me data where they have not fixed the scales, and so when you look at them, you know, they're going from max minimum, so each of the plots is not starting from 0, and so when you flip from one plot comparing to another plot, your eyes are not quite reading it correctly because each of them is plotted to a different scale. So it's really important to fix the scales, you know, lock them down, so that when I go from one plot to the next, and here I'll do it, if I go from one to the next, you know, you can see that they're all the same scale. It's just the data that's changing. So that's one of the first things you want to do. And then the next thing you want to do is, well, I'll go through the range of plots. So you've got the raw data plots here. So there's a bunch of tabs at the bottom for the basic plots. So I've got tip resistance, sleeve friction, and pore pressure. That's the raw measured data. And because I had loaded in some dissipation tests, and I'd chosen the option to display them, so you see a little blue arrow here that shows where each of the dissipation tests were performed that I had loaded in. And the blue line is showing the hydrostatic line. And I had previously set the water table for 2 meters down, which is what the dissipation tests had told us it was. So I've already fixed the water table. But the other set of plots is, you know, the basic plots would be corrected tip resistance, friction ratio, pore pressure, and then the soil behavior types using the traditional non-normalized chart, which I had sort of updated in 2010. And then there's a set of normalized plots where it's been normalized for overburden pressure, and so you've got the normalized soil behavior types. Now, of course, to do the normalized, obviously the program's done some calculations, and it's and so you need to interact with it a little bit on what exactly the calculations it did. So there's a button up here called CPT Properties, and if you do that, it starts to show you what your options are. And one of your first ones is the ability to do an averaging. It's a rolling average, so it doesn't remove any of the data. It just smooths the data out. The program defaults to a rolling average every 3 data points. But if I go down and I put it back to 1, so that means there's no rolling average. And if I apply that, you'll now see that, that if I go between the raw data and the basic plot, they're exactly the same. There's no averaging. So if I go back to the basic plot, now you'll see that if I go and apply an averaging, so we're going to look at this plot of tip resistance. So I'll put an averaging, say, of 5 on, which is a little bit larger. So you'll see a slight smoothing out of the profile. So if I now apply that. And also you might want to look at the soil behavior type on the far right here, where the computer tries to write in the various soil types. And you can see that when you're using every data point, if the soil type is right on a boundary, it keeps switching from one to the other, and so the computer's trying to write more words in. Whereas if I do some averaging, you'll see that this gets smoothed out a little bit, and it's got more space to write the words. So you'll see that. So look at the soil behavior type here in the words, and also look at the chart here. So if you look at the plot first, when I apply it, you'll see it got smoothed out a little bit, and the words got thinned out a little bit more. If I apply a slightly larger average, say every 10, and apply that, you'll see now it got smoothed out even more. So if you want to use this plot on the end to put maybe in a cross-section, sometimes you might want to smooth the profile out so that it looks a little nicer in terms of words, and it's capturing sort of the big layering and not getting too much detail in there. So you can see it smoothed the profile out. But I'll go back, for now I'll go back to just sort of the default of 3, and that will get applied to all of them. And that's still getting a lot of detail without losing that detail, and I've got reasonable profiles here. And then I go, I'm going to go to the normalized plot. So let's go a little bit further. We have the averaging. So if I knew what the ground elevation was, I could put it in. Or if I don't know what the elevation is, I just know what the relative elevation. And there's 3 here. Let's say 2 of them were basically at the same elevation and 1 was a couple of meters higher. Then I could put 2 of them down as 0 elevation, and the third one that was 1 meter higher, I could put an elevation of 1. And so it would be separated in elevation by 1. And the reason I want to do that is that there is a button under the reporting feature that allows me to look at overlay plots. So if I select overlay, I get an overlay of all the, I've got all 3 of them selected, and they're all selected up here. And so here is the overlay plot. So here it's showing tip resistance, friction ratio, pore pressure, and the non-normalized soil behavior type. And I can toggle on and off, so I can switch one of them off if I want to just compare how it matches. I can do that with any one of them. I can change the color just by clicking on the color box and say, maybe I'll go for a lighter green. And you can see that I'm not a big fan of the lighter green. I go back to the dark green. So you've got a lot of flexibility, and all the plots are here. I'll go through them later, but they're all there, and you can print out a report. So I'll come back to that later. So let's go back to the CPT data and the properties and work our way down. So we talked about elevation. I put in the groundwater at 2 meters. And at this particular site, groundwater conditions are approximately hydrostatic, so that hydrostatic line is not bad. But if the dissipations had shown that the groundwater conditions were not hydrostatic, I have an option to input that non-hydrostatic groundwater condition. So I would select non-hydrostatic and then press the tune button, which would then say, okay, put in a table of the values. So if I'd had a series of dissipation tests and I determine equilibrium water pressures from those various dissipation tests, I could actually put those values in and apply it, and then it would adjust, instead of just using the hydrostatic, if I move that out of the way, instead of having that simple hydrostatic line to calculate the pore pressure and hence the effective stress, it would actually use whatever non-hydrostatic profile that I had at the site. And then for dissipation tests, it wants to know the radius of the probe, and this was a 15 square centimeter cone, so I'd already put in that it's 0.022 meters. And these cones have a net area ratio of 0.8, so that's in there to calculate the corrected cone resistance. I'll come back to this transition layer detection later. There's a button here that if the file that you had loaded in already had the corrected cone resistance, you could select this and then it wouldn't be trying to make a further correction. If I scroll further down, I've got the unit weight of water. Now, of course, it defaults to fresh water, but if I was doing water in a saltwater environment, I could change the unit weight of water to a slightly heavier value for salt water. And one of the key parameters is the unit weight of the soil, and I've got it selected to automatically estimate the unit weight. Or, of course, you can go with a single value. Here, it's in SI units, so it's showing 19 kilonewtons per cubic meters. Or I can click the box, and I could actually input a table of values that would represent the variation of unit weight with depth. So if I'd taken samples and I knew what the unit weights were, and particularly if I had say a soft organic layer where the unit weight might be exceptionally low, then it can be quite important for you to put in the correct one. But often as an initial first analysis, it's useful to automatically estimate it. So that the program will estimate the unit weight based on a method that we had developed some years ago, which is basically based on the soil behavior type. And essentially, the denser, the stiffer and stronger the material, the likelihood it's a little bit denser and therefore a little heavier, and the softer the material, the likelihood it's a little bit lighter. And if you want to check what unit weights are used, then you can actually go and look at the unit weight column up here. Now, this particular one, the upper 1.5 meters was hand augered, so you can see it's got this -999 in there so that it gets filled in as hand auger. But if I scroll down, this is the column of unit weight here. If I scroll down, you'll see it start to change, and on average it's around 16 to 17. Another way to look at numbers is one of the features the program has is if I press the Shift key and go to any one of the plots, it'll actually go to that value. So you can see that if I hold the Shift key down and I go to one of the plots, it will actually go to the digital data at that location, so I can actually look at the number. And so if I move my eye over to the unit weight, you can see it's a way of scrolling down the column of data. Here it's friction ratio, and here would be pore pressure. It would go to those values. So it's quite a nice feature of if you actually want to look at the individual numbers. So we'll go back to the soil properties. So we went for auto unit weight, and then you put in the constant for OCR, the constant for undrained strength, and the constant for relative density, and the constant for sensitivity. Now there is a little one, this CN cutoff. In the liquefaction world, often they limit the normalization exponent CN at very shallow depth, and it's normally 1.7 or 2 that they limit it to. For CPT interpretation on regular stuff, that's not normally done, but the program does have an option that you could limit that if you wanted to. And there's also a little button up here which comes from ground improvement to make a slight shift in the IC. And we covered that in the webinar on ground improvement. Then there's one little button down here that it's also going to estimate the SPT-N value, and it defaults to N60, but you can look at N160, the normalized N60 if you wish. So those are all the parameters that allows all the interpretation to be done. So interpretations like for modulus, it's built in, so actually there is no constant, so you don't get to change it very much. So I'll go through the plots. We saw the basic plot, and then you got the normalized plot. And then in the previous webinar, I had talked about updating the soil behavior type chart. So here's the regular soil behavior type charts. The one on the left is the non-normalized. The one on the right is the normalized. It's normally, the normalized one is the one I recommend that people use because these are relatively deep soundings. They're 30 meters or 100 feet. And so the deeper you go, the more important the normalization gets. And you can see that on the non-normalized data chart, the data's drifted upwards because of the increasing depth, where when it's normalized, it pulls it back down and shows that it's predominantly clay, silty clay. It's a slightly stiff silty clay. You'll see that later. It plots further down. So another feature, again, if you press the Shift key and click on one of the charts, it'll actually tell you what depth each of those data points are. So if there's a data point that you particularly want to know and say, well, where is that data point? This particular one's at 29.6, and it's taken me to that data across the top. So I can actually have a look at the values. And I can always go back to the plot and say, well, where is 29.6? Of course, 29.6 is just as it's going into that sand layer. So it's transitioning from the clay into the sand layer. So there's the charts. Now, in the previous webinar, we had talked about updated charts. So the updated normalized soil behavior type chart. So here it is here on the left. So a slightly more hyperbolic shape to the boundaries, and I've added in the dilative contractive boundary. So it's moving towards more behavioral description. So you've got sand-like dilative soils and sand-like contractive soils. You've got clay-like dilative and clay-like contractive, and then you've got clay-like contractive and sensitive, and you can see that some of the soils are falling in that clay-like contractive. Some of them are beginning to fall into the transition zone. And here's the modified Schneider plot, which uses the excess pore pressure parameter, normalized excess pore pressure parameter. And you can see most of it's plotting clay-like, with some of it going up into the transition. Now the one on the right here is the one we talked about in the last webinar, which is based on shear wave velocity. Now these were all seismic CPTs, so I had imported the shear wave velocity so that this could calculate. And how I did that is that there is a custom estimate button up here. If I open that, what it is, it's like a spreadsheet table that allows me to import additional data that I may have measured. So I'll make that a little bit bigger. So here, the only data I've imported is actually the shear wave velocity. So I put in the various depths and the various shear wave velocities. And how I did that is, for Gregg, the shear wave velocity is presented to clients in a spreadsheet. So I just simply go to the spreadsheet and I cut and paste the depth column and I paste it in, and then I cut and paste the shear wave velocity data and I paste it in, and then I say, okay, display it on the plot. And then when I say okay, if I actually go to the estimated parameters plot, I'm going to skip to the last one, you'll see that this is where the black line is the estimated shear wave velocity from the CPT, and the red one is the measured shear wave velocity. You see on this particular case, they actually agree really quite well. So if I go back to that updated normalized soil behavior type chart, you can see that the data is falling within that band of this normalized rigidity index, this kg value, between 100 and 300. And that's where most young, uncemented, well-behaved soils tend to fall. And so this data is falling right in there. So it's saying the soils at this site are relatively young and appear to be uncemented, and that's consistent with the geology of this site, that we are in fact expecting a sort of a Holocene age deposit here, which is relatively soft. It's mostly clay with some interbedded sand layers, and sure enough, all the shear wave velocity data combined with the CPT is falling within that band. In fact, if I quickly flip through all three of them fall within that band very nicely. So it's a nice confirmation that says, yes, the soils at this site appear to be well behaved, they're young and uncemented. So we would expect these correlations, both the soil behavior type and the various parameters, to work quite well, because these are well-behaved soils and they're consistent with a lot of the soils that the empirical correlations are based on. So we would expect the interpretation overall to work quite well. So a nice feature that the program has is that, so here's the normalized profile. Let's go to, they're all about the same. Let's go with this one. So this soft clay layer right at the bottom, it's probably the softest. The normalized value is getting smaller. If I left click and scroll, so I can zoom in on the profile. So by left clicking and scrolling, I actually zoom in on the profile. Now the nice thing about zooming in on the profile is now I'm just looking at that part of it. Now if I go back to the soil behavior type charts, it only shows the data that I zoomed in on. And here's the updated one. So, so you can see that the lower clay is, a softer, normally to lightly over-consolidated clay, and it's actually slightly sensitive. It's falling into that sensitive region. And of course, it's also plotting as a clay for the pore pressure, and the few shear wave velocity measurements, there's only 3 of them down in that little interval, is plotting with a low kg, saying, yeah, this is a relatively young, still a young uncemented deposit. So you can do that with various parts. So the upper clay layer, which is a bit stiffer, I can zoom in on that portion, and I can also zoom a second time. So you see the pore pressure drop there. So I'm just going to zoom in on one portion of it, and go back to the chart, and you see now it's plotting higher. It's plotting into the transitional zone, sort of a more siltier transitional material, transitioning from one that's either clearly sand-like or clearly clay-like into, it's transitioning from either sand-like to clay-like. And certainly looking at the profile, and we'll look at the dissipation test, it is generally more clay-like, but it is siltier, so it's falling into that transitional clay-like material. And even on the pore pressure, it's still within the clay-like zone of based on excess pore pressure, but it's a little stiffer. So that zoom feature is really quite a nice feature, and the way to get out of it is to zoom in. I would left click and scroll down, and to get out of it I left click and scroll up, and that gets me back to the full image. Of course I could have just adjusted the depth. I could have said, oh well, why don't I just look at the plot from one depth to another depth, and that's a way of zooming in. It's just a little slower. It's certainly faster just to click and zoom straight in. So I've gone through the basics, the basic plots. I didn't go through the estimated parameters, so there's a tab up here, and there's a number of there's 3 different sets of tabs of parameters. Just like version 1, you've got the first one is a plot of estimated soil permeability versus depth, and it covers 10 orders of magnitude here at the bottom. So it's from 10 to the minus 2 to 10 to the minus 10 meters per second, so that's a big range. And this is based just simply on the soil behavior type. So if it's clay-like, it gives it a low permeability. If it's sand-like, it gives it a higher permeability. And the next plot is N60. And so again, if we had measured N values, let's say, I'll just make up some numbers here. I'm just making them up as I go down here, just to illustrate. So you'll see now it's put those values in. So if you had measured SPTN values, that's a way of comparing it. And the next plot is the Young's modulus in sand-like soils, and there's a little bit of sandy material at the top, and then the sand layer in the middle with some little thin sand layers down. And then relative density and the peak friction angle. And the next set of plots show the one-dimensional constrained modulus for settlement calculations, and you can see that the clay has a much lower one-dimensional constrained modulus than the sand does. And then the next plot is the small strain shear modulus, and then the next plot is the undrained strength, the black line being the peak undrained strength, and the red line being the remolded undrained strength. And of course the peak undrained strength is coming from the tip resistance and the MKT value that was put, and we had gone with the default value of 14, so there it is there. And the red line is the remolded strength, and that's simply just based on the sleeve friction. So it's assuming that the sleeve friction is an approximate measure of the remolded strength, so you can see the peak and remolded. And then the next one is just the undrained strength ratio, the peak undrained strength expressed as a ratio, which is often a nice thing to look at, because of course undrained strength may vary with depth, and for normally consolidated clay it would increase with depth, but the undrained strength ratio will stay constant. And then of course the far right is the over-consolidation ratio, and you can see that the upper clay is more over-consolidated and then gradually becomes lightly over-consolidated at the bottom. So the bottom clay is an OCR closer to about 2, and then the upper one, it's more variable, obviously maybe a little bit more sandier with quite a bit of variability in there, and OCR is up around 5. So it's more dilatant to the top, more contractant at the bottom, and that's consistent with that updated soil behavior type chart. And then the last set of plots is the shear wave velocity, which we had looked at, the red one being the measured shear wave velocity, the black estimated, assuming that it was a young, uncemented silica-based soil, and so you can see the two are comparing reasonably well, which is consistent that this is predominantly young, uncemented deposit. The next one is state parameter for the sand-like soils. The next one's the K0 in the clay-like soils, and then the next one is sensitivity, and that's based on that factor that was put in, the sensitivity factor related to the friction ratio. And it says, on average, the sensitivity is around 4 to 5, which is actually quite a sensitive material. And then the one on the far right is the effective stress friction angle for the clay-like soils where there is a positive pore pressure. And you can see that it says that the clay-like soils, the lower one, the peak effective stress friction angle, assuming zero cohesion, is around sort of 33 on average degrees, and the upper stiff one is a little bit higher. And where it's dropping down, that's where it doesn't apply to sand-like soils, or it doesn't apply where the excess pore pressure, it goes negative. So that's a quick review of all the plots. So you can see this is a site where it's predominantly clay with some sand layers, or fairly major sand layer from about 15 to 17 meters, and then some little smaller sand layers at depth. And these smaller sand layers are less than a meter thick, so they're quite small. So in general, sort of a stiffer, over-consolidated, sort of silty clay near the surface, obviously sandier in places where the pore pressure dropped. Maybe it's a little sandier there. And then you've got this predominant sand layer and then some thin sand layers. And remember when we went to the overlay plot, it's pretty consistent across the site. And the overlay plot includes the normalized plots as well as the parameters plot. So you can see, for example, how consistent the undrained strength is. And at this site, it's very consistent across the site. Let's go back. Now, one of the features that I went by was under the properties, you have an option to remove transition layers. So, for example, it's clay and then it goes into the sand layer. And when it goes into the sand layer, or these very thin sand layers, the data is caught in transition. If I zoom in, like these, if I zoom in on these sand layers here, you can see that you're in clay and then it goes into the sand layer and the data transitions in, and then it transitions out back into the clay and then back into another sand layer and then back down again to the clay layer. And because these sand layers are so thin, it may not be reaching the true value within the thin sand layer, but it is identifying that it's a sand layer. But when I go to like the plot of undrained strength, you'll see that you get these tails where the data is transitioning into the sand layer, but it still gets interpreted as a clay, so it's interpreting undrained strength, and you get these tails that can make, sort of the visual presentation of undrained strength a little bit deceiving. And so if we go back to that soil parameters, if I select the auto transition layer detection and then I tune it, what it tries to do is it tries to identify these transition layers, and you can adjust how aggressively it looks for it by sliding this bar up at top. You can adjust how aggressively it looks for the transition layers and how many data points it's going to base it on. Basically what it's doing is it's looking for data that's crossing that boundary between sand-like and clay-like, which is roughly at an IC of 2.6, which is that line down the middle here between the dark green and the light green. And so anytime the data crosses there, it says it could be a transition zone. And so if I apply that, now if you look at the plot of undrained strength, so I'm going to apply that, and here's the plot of undrained strength. Now if I say, okay, apply that, now you'll see much of those tails will disappear. Now of course the zoom in also disappeared, but you see that the tails have generally disappeared, and now it looks a little cleaner in terms of showing me what the peak undrained strength is in the clay without these sort of confusing tails that those little sand layers create. So it's quite a nice feature to either add or subtract to see how much effect. So I'll now take it out and you'll see it come back. Now if you look at this plot here, you'll see the tails come back. So clearly that's where the sand layers are. You can see them clearly here. And so it's often nice to remove them to make the interpretation a little bit clearer. So those are the basic things. Okay, we'll now go over maybe the dissipation interpretation. So there were dissipation tests. So let's go on CPT1 first. So there were roughly 3 dissipation tests per sounding, mostly in the sand layers. The focus was to get the equilibrium water pressure, but some of them were in the clayier zones. So the first one was at 3 meters. And here's the dissipation test. You can see it started at a negative value, rose up, and then decreased and actually comes to equilibrium. So, when I put that 2 meters of water table in, it's matching the equilibrium quite well. If it wasn't, you do have the option to move the equilibrium water pressure. You can find where it best fits if you want to adjust the groundwater table. And this is a plot of pore pressure against square root of time. And what's nice about choosing that is the interpretation is that ideally it would be a straight line dissipation and then curve over to equilibrium. And so the best way to interpret it is there's a button up here to draw a line, and you draw a line to the dissipation. Now this one's a bit complicated because it rose up before dropping down, but what it's basically saying is the pore pressures were negative behind the tip, but they're generally positive around the cone. So they rose up and then started to decay. So you can see by drawing a straight line through that portion, it's going to extend it back to what it would have assumed the initial pore pressure would have been. And based on that, it calculates the T50 and gives the CH and the permeability based on, in this case, the rigidity index of 100. And you can adjust that. There's a button up here for settings, and you can go to calculation settings, and you can adjust what the rigidity index is used. I had put in 100 and told it to apply it to all of them. Now, if it's a clay-like material, it does in fact try to calculate the rigidity index. Here it's not clay-like, so it's not giving a value, but it will try to do it for you if you want to compare, what an estimate would be as opposed to just using a sort of a standard number. Here I chose the standard number of 100. So if I flip between them and I fix the scales again, so I had fixed the scales and I'd set them all to be the same, and so if I go between them, okay, I haven't set them to the same. That's because the pore pressure is much higher. You can see I've got the interpretation on all of them here. So here's one that's in a more clay-like. You see it's much slower. If I take the interpretation off, you do have the option to plot on a log scribe. So if I just click on the axis at the bottom, I can switch over to a log scale and go, say, from 1 to 10,000 seconds. And now you'll see the plot in the more traditional log time plot. And so one of the nice reasons about going square root is it projects to where it thought the starting point was, because a more theoretical curve would come up and the starting point would be up around 500 kPa, where in this one there was a slight rise before it decayed off. So I'll go back to square root. I forgot what I have now, 50, there we go. And you can see the interpretation I went as I drew a straight line portion. I'm doing it rather quickly here. And then ask it to calculate, and it extrapolates up to the initial starting point, and it's calculated the T50. And you can see if I actually move U0 around, if you want to see how sensitive the results are to U0, you can just slide that number around and you'll see T50 changing. You can see that T50 is not overly sensitive to any small errors in your estimated equilibrium, so it's not that big a deal if you're slightly off. And then on the right-hand side, you can see it's plotted the equilibrium as the triangle, and then the assumed initial starting point, the actual starting point, and then the T50. So it's all labeled down at the bottom here. So there's quite a lot of detail on how it can do the dissipation test for you. Now, I'll go to some of the other features. There are some interesting design features that the program has. One of them is you can estimate bearing capacity. So you just put in the range of footing width. Here it's defaulted to 1 to 4 meters in steps of 0.2, and it's going to calculate it over 1.5 times the width of the footing. It's using the average value of 0.2. Since it's mostly clay, I could go with the clay value of 0.3, and it'll calculate, and if I just adjust the scale, you can see you get a plot of the ultimate bearing capacity as a function of the width of the footing, and on average it's sort of between about 500 kPa and sort of maxing out at 700 kPa. So on average around sort of 500 to 600 kPa is the ultimate bearing capacity of a strip footing of somewhere between 1 to 4 meters in width. So based on that, you might want to do a settlement calculation. And let's go back to the basic plot so you can see what we're looking at. So I can do a settlement calculation. And so let's say, okay, we have a 4 meter rectangular footing. It can be circular or it can be strip footing by making this number a lot bigger, L over D. And so we said it was about a 500 kPa bearing capacity. So let's say that if you put a factor of safety of 3 on that, maybe about 150 kPa as the bearing pressure. And since we have no data in the upper 1.5 meters, I'm going to embed it 2 meters down. And I'll ask it to calculate. So here's the graphical presentation, which is the cone resistance, the one-dimensional constraint modulus, and if I say calculate, it'll calculate the settlement of, let's change the scale a little bit. So here's the profile of settlement versus depth for that 4 meter wide rectangular footing, no, actually square, so it's L over B of 1, so it's a 4 meter square footing, it's flexible, I haven't removed the soil above, and I've applied the 20% rule, which is I'm only looking at where the change in the stress exceeds 20% of the existing stress. I can remove that and it'll calculate it all the way down. And so you can see it didn't change the result a little bit, it's just picking up a little bit of settlement in the lower clay. But you can see most of the settlements in the upper clay because after all it's a 4 meter strip footing. If I made it 10 meters, like an embankment, obviously the numbers will change. It got quite a bit bigger. Let's go back to 4. So you get a settlement profile, and if you were thinking about, well, where do I need to get a sample to verify how adequate this settlement calculation is, then you can see that most of the settlement's up around 5 or 6 meters, and so it's in that upper stiffer clay that you would need to get a sample to verify the settlement, and maybe a sample of the softer clay down below just to check what the OCR and the settlement would be down there. But most of the settlement's going to be above. So if I apply that 20% rule again, I can add a bit of creep settlement. So if the primary is over in 6 months and I'm looking at 5 years, using Mesri's simple calculation, it tries to estimate what the additional creep settlement. And because this is a stiffer over-consolidated clay, it says the expected creep settlement in that upper 10 meters is going to be pretty small. These are not perfect calculations because after all it's estimating the one-dimensional constraint modulus, but the updated correlation for one-dimensional constraint modulus is a lot better now than it used to be 5 years ago. So experience shows that these calculations are actually not bad. It is sort of the right magnitude, and it's certainly giving you the right sort of profile, which can be very helpful. And then likewise, if you wanted to estimate pile design, you can come into the pile design method and you have to put in the pile details. So maybe we'll go for, well, it's defaulted to 0.8 of a meter, and we'll switch it over to group 2, which is a driven, maybe a driven concrete pile, driven precast pile 2A, and ask it to calculate. And again, I can just adjust the scale a little bit. And this is allowable pile capacity with the standard factors of safety that the LCPC method applies, which is 3 on the tip, 2 on the shaft. And so the red line is the accumulation of shaft resistance, the blue line is the added base resistance, and you can see when you encounter that sand layer, there's quite a bit of added base resistance comes on. So you could drive the piles down to about 15, 16 meters into that sand layer, but the difficulty is you'd actually be sending the load further down and closer to the underlying soft clay. So actually the settlement of the pile group actually could be quite large because you'd be sending the load further down into that softer clay. So on this particular site, you're probably better to not do that. But you can see that this sort of tool gives you the ability to very quickly look at some of the variables. So let's go to the reporting. Oh, before I get there, so I went through dissipation, settlement, pile. There is another feature in Europe. they quite often like to determine a typical geotechnical section. So if I select this, what this allows you to do is actually determine sort of major layers and calculate average parameters within the layer. So let's say from 0 down to 14 meters, I'll call this layer 1, and I could give it a name. Maybe I'll the upper clay, but it could be a geologic name. And then, of course, from 14 to 17 is the sand. I'll call that layer 2. And then from 17 all the way down to 29.5, I'll call that layer 3. And boom. So what I've done is I've sort of, and you can see the values it's calculated, so the average values it's tried to apply. So I've got this upper clay, the sand, and the lower clay. I'm ignoring these little sand layers. And if I go to the report, it produces a report based on those layers that I've defined and presents sort of representative value, average values within that layer. Now I went with average. I could have gone with geometric mean by selecting this button up here and saying, no, I want geometric mean instead. And I can also go and look at the layer list, etc. And then if I do that on every one of the CPTs, there is a button that allows me to look at the statistics of all those layers on all of the CPTs. Now I've only done it on one, but I might say, show me what the statistics is on layer 1. Now, of course, I only did one, so it's going to basically show me the same sorts of values I had before, and there's a reporting feature where it would summarize all of that. But if I'd done it on all 3 of them, it would have done a sort of a summary of that layer in all 3 of the CPTs that I had selected. So that's quite a nice feature. And it's used quite a bit. Eurocode requires that you identify layers, so that's partly why it's there. And if you're a little bit uncertain about how you define the layers, there is sort of a quick section maker that will try to do it for you. So you have to group the numbers together a little bit. And it's based on statistics, and so it tries to go through it. I'm going to flip it to IC. And so it tries to do it for you based on statistics. Okay, let's go back to that one. That one is not bad. Maybe it's the one. Yeah, this one. So that many data points. It does actually not a bad job. You can see it's sort of saying, yeah, okay, it's mostly a clay layer, then a sand layer, then a clay, and boom, it's actually done it reasonably well. Of course, we hand ordered the upper 1.5 meters, so there's nothing up there. So it's like a wizard that tries to do it for you. Now, if you've done that, if you've selected the colors, which I had done, if you go to the soil behavior type charts now, it actually color codes what I had selected. So, you know, well, of course, I selected a similar color for the upper and lower clay. It's only the sand that was brown, and most of the sand is up here. But there are some portions that are going down because when you look at that particular sand layer, it's not a homogeneous sand layer. There's a little softer. It's really 2 sand layers. And so by going with a broad averaging, it was a little bit crude. But you have that ability to determine the geotechnical section. And under reporting, under the reporting button, I'd already shown you the overlay feature, and you can produce reports of that. So here's all the plots of the overlay, which is quite nice. So you can go to the report setting, decide what plots you want, and so here I've selected like well, we could go with the basic interpretation and the normalized ones. We'll just go with that and say, okay, I'm happy with that, and maybe I'll just do a single one, and it'll just show me a set of plots for the single one. Or I could say, no, show it to all of them, the overall report, and it'll do it for all 3 of them, and I get a complete set of plots. So you've got quite a lot of choice of the type of plots, and of course if you want the dissipation report, I can choose Other and select Dissipation, and then it will give me a report for the dissipation test. So there's the little table. It's with my interpretation, so you've got the T50 values and the coefficient of consolidation. It shows me each of the plots with my interpretation on there. And a nice feature is you can actually produce a custom plot. So you can go to custom page and you can actually generate your own set of plots. So you get to, with a drop, so plot number 1, I might say, okay, I want to see the tip resistance, and then maybe I want to see the soil behavior type, the normalized one, and then maybe because it's mostly clay, I want to look at undrained strength, and then maybe OCR. So I'm producing a custom plot here based on these parameters, and I can preview it. And so there it is. So I've got tip resistance, soil behavior type, undrained strength, and OCR. And I might say, I actually like this plot. I'm going to use this on the project. So what I can do is I can actually save the report, give it a name, it gets saved into the file, and I can either call it up by load the report, or under the report settings, I can select custom page, and then I go searching for the one that I want to use, and I select it, say OK, and then if I do the overall one, it'll produce that custom report for all of the CPTs there. So you can see pretty powerful. And so some extra features that I didn't cover, one of them under the project and project parameters, I said display settings. I've got the option where I can put the groundwater table on all of the plots, and I can also color in under the tip resistance. So it takes the soil behavior type colors and colors in under the tip resistance. So here's the normalized one, here's the non-normalized one. So in terms of the normalized one, what it's done is it's taking the soil behavior type colors, so the sand layers get colored in brown, and the clay layers, these are silty clays, so they're colored in sort of dark green. And so it actually color codes the tip resistance profile. And that idea actually came from ConeTech in Vancouver. They did that, and it was a very nice feature, and it can make the plots look quite attractive by opting for that. So if I go to the report, sort of go for like the standard plot, you'll see that now, of course, it shows up in the report. So it can make the plots look a little bit nicer. Now another feature is every one of these plots can be exported. So if you just double click, you've got the option to export as a graphic. So if you want to export this and put it into some of your software that you might be using to develop cross sections, you can export any one of these things to put onto your cross section. You can also export the data to an Excel. So if it's just the basic data, you can export to an Excel file, or if it's the estimated parameters one, you can export that to an Excel file. Now there's also a button here that says Google Maps, and so under the CPT data, under the properties, there's an auxiliary information. So if you knew the GPS positions of those locations, you can type that in, and then under the Google Maps, you can actually then add the CPT, which I've already done. And so you can see these 3 CPTs. This is a fictitious site. It's not really. It's actually close to where I live. My house is just around the corner here. So I'm sat right now right in this house here, and I fictitiously located these 3 CPTs in the nearby park near the nearby school. And you've got the option for a satellite view if you would like. So you can add the CPTs onto a map, and of course then print that out to your report. So you can see that there's really quite a lot of features that the program has, and I think I've covered most of them. Ones that I haven't, and we're running out of time a little bit, is import DMT data. So if you did some flat plate dilatometer at the site, you do have the option to import it, and it asks you what format it is. The standard output from the DMT is a .uni file, or sometimes it's in Excel, so you can import it in, and then you would get a series of plots. The first set of plots would be the standard DMT plots, and then the next ones would be where you could compare the DMT and the CPT side by side. So you'd have like the CPT plot of soil behavior type, and then the DMT ID, etc. So it's rather a nice way of comparing the data. And there's a couple of parameters that Professor Marchetti has suggested. which is this sort of the DMT-M over the CPT-QT as a way of sort of identifying unusual materials. And so it allows you to look at those ratios as well. So hopefully, I know I went quite quickly there, and it was partly because we got a little bit of a slow start, but hopefully I've been able to show you a lot of the features that the software has, and version 2 is similar to version 1. It's just got a couple of extra features, one of them being this, the new soil behavior type charts, and I didn't actually show you the profiles. So here's the profiles of these normalized parameters, so normalized friction ratio, normalized pore pressure parameter, and then this normalized, the updated soil behavior type IB, and then the normalized soil behavior type descriptors, where it talks about clay-like contractive and clay-like dilative and sand-like dilative, etc. So if I just do a little bit more averaging there, so you can see the words maybe a little bit better. You can see the flexibility that you've got with the new charts. So there's a few new things in version 2 that didn't exist in version 1, like these new charts, the updated charts, like the ability to add the DMT data. It's also got the ability to import this hydraulic profiling tool data, which is a device sold here in North America that's a probe that measures electrical conductivity as well as the pore pressure to inject a small volume of water into the soil. And so if you've got unsaturated soil, this is quite a nice way to sort of get a pore pressure profile in unsaturated soils, because you're trying to inject water into the soil and you measure the pressure required or that's created as you try to inject it in. So of course if it's sand, it goes in very easily, the pressure is very low, and if it's clay, the pressure builds up very high. So you get a sort of it's like a pore pressure profile from the cone, but it works in unsaturated soils, and so you've got the ability to import that as well. So what we'll do now is we'll switch over to some questions. So I'll keep this profile open because the questions might revolve around some of it. So first question is, can version 2 correct depth for inclination? And the answer is yes. Underneath CPT data, there's a couple of buttons in here that allow you to change things. And one of them is actually a depth inclination. So it says depth correction filter. And if you select it, what it will do is it says this filter assumes that the inclination data were imported in the other column. And so if you'd imported inclination in, I think in degrees, then it will automatically adjust the depth. So, when we imported the data, it asks for, depth, tip, friction, pore pressure, and other. And so if you have inclination, or if you've calculated it, based on the inclination from the cone, so you added a column of data, then it'll import it in, it's in degrees, and so it would correct the depth based on that inclination. So yes, there is a feature to make that correction. There's a couple of other features of corrections. One is a thing called here a spike removal. And so if you've got some data where maybe it was hard pushing and the rod breaks have not all been automatically removed, and so you can see a lot of rod breaks in the data, you have an option to remove those. There's none here, but what you could do is say, yes, apply the filter to like the tip resistance where the rod breaks are noticeable, and you ask it to smooth out those rod breaks. So that's one of the features it has. There's also a little feature where you can do a quality control on the data. And what it does is it looks for negative values on the tip and friction, or zero values. So oddball looking data, and of course if I do it here, it says, hey, the CPT looks good. So the data's good on this profile. There's also another one that, when it was estimating parameters, first of all it said, well, is it sand-like or clay-like? And basically it said, look, if it falls into, let's go back to it. So if it falls into regions, 5, 6, and 7, and 8, it says it's sand-like. If it's in region 1, 2, 3, 4, and 9, it says it's clay-like, with roughly that IC of 2.6. But it actually bases it off the chart. So If it falls into those zones, it's either going to be treated as a sand or a clay. If you don't want it to do it exactly that way, so here, for example, you know, this upper clay is sort of, it's mostly falling into the clay-like region, which is why it's successfully calculating undrained strength, okay. But there is a button up here that allows you to adjust that. And so it says, okay, do you want to do it on, it defaults to the soil behavior type zones using the normalized chart, but you can switch it to IC and you can adjust the IC. So if you wanted more of the soil to be treated like a clay, I could adjust that to 2.5 and display it on the chart. And it just would add in a bit more data as clay-like. Now, clearly, that's not what you want to do here because it's picking up more of the tails in the transition zones. But in some soils, you know, you can see it's just moved the cutoff over a little bit. Or I can go back to the soil behavior type zones. So you do have some control over how it picks whether or not you want to calculate clay-like parameters or sand-like parameters. So another question, is there an example of a non-hydrostatic profile? Yes, there is, and I think I covered it, maybe I covered it under one of the webinars on dissipation tests, but I probably won't be able to find one here. But there are numerous ones. If I go back to the basic plot, there's a hydrostatic line. And so if I just quickly illustrate, if I go and say it's non-hydrostatic, I'll tune it, and I'll exaggerate here and say, okay, at 2 meters, it's 0, so I'm keeping the water table at the same depth, but I'm going to say, well, down at 30 meters, I'm going to put in, let's say, a much higher one, like 500 kPa instead of the almost 300 it comes out. I add that value and then say, okay. So if I just move this out the way, so here's the existing hydrostatic line in blue. If I now apply this, you'll see it get moved over. See? It got moved over. And that was just a very simple straight line portion. And you can take it off by deselecting it, and it goes back to the hydrostatic line. So yes. Next question, is CN cutoff automatically applied to slick? Yes and no. Slick is a liquefaction program, and a lot of the methods have a CN cutoff, and usually it's 1.7. And so if you selected a method, yes, it automatically applies it. But if you go into the advanced parameter tab, you can unselect it. You can forcefully say, no, I want to see what would happen if I took it off. And of course, it usually only influences the upper couple of meters of data where the effective stress gets very low. And so you can toggle with it on or off and see what the effect is. Next question, can you enter a water table above the ground surface for offshore? The answer is yes. Typically for offshore water, the data is zeroed at the mud line. That means it's automatically taken off the water. And so if you do, if the contractor has done CPT where he zeroed the cone data at the mud line, then you would put in the water table at 0, because that would give you a 0 effective stress at the mud line and everything would be correct. So if I go to the table, if I go to 0 depth, you'll see that the effective stress is essentially 0 at the ground surface. I mean, the first reading is 5 centimeters down, so it's not exactly 0, but you can see it's very close. But if the contractor had taken the 0 load readings at the water surface and then lowered the cone down through the water, then the cone is measuring the water pressure. So then you have to put in the water table above, and so then you have to put it at minus, I'll put 2 meters. And it's gone off the plot, but you can see that the hydrostatic, if I exaggerated it a little bit, I'll go minus 20, so now it'll be exaggerated. And so now you can see it's, so, and the way to check if you've got it right is you again go to the ground surface and you check that the effective stress is being calculated at 0. So now what you've got is you can see that the total stress is the weight of water and the pore pressure is the weight of water, because it's actually added the 2 on, so it's still getting an effective stress of 0 at the ground surface. So yes, you can put in a water table above. I'll go back to 2 meters down. Explain cross-correlation. Yes, I didn't explain that. On the raw data, so you've got the raw data, tip, sleeve, and pore pressure, and this little plot is a cross-correlation. And that's because there is a physical offset between the tip and the sleeve. The sleeve is behind the tip. And so it's about nominally 10 centimeters behind the center of the tip. And so at any given time, the data is not at the same depth. And since the data file is in terms of depth, the manufacturers of the cone usually take that physical offset and offset the data so that the data is truly at the same depth. And this little cross-correlation plot is essentially doing a cross-correlation to see how well that actually works. And you see here, it's saying it's working pretty well. You're getting a nice bell-shaped curve. It's roughly around zero depth increment. It's sort of saying it's 1. So if I go between them, they're all showing, they're all showing 1 increment. So what it would say is that you could adjust it and you'd get a slightly different friction ratio. And you do that with a button up here. It's the very first button up here that says the cross-correlation filter. And if I select that, it's saying, do you want to shift it? And if we do it, I'll say yes, and you'll see it'll get moved over. So it shoved it over. And so the only thing that got changed was the friction ratio. And on this particular profile, it really hasn't made much difference. And from my experience, generally it doesn't make much difference. The standard physical shift difference does give you reasonably good answers. There are some profiles where it might make a bit of a difference, but in this particular one, the data's correlating quite well. It doesn't make much difference. Next question. If you move the U0 line in the dissipation test, does the groundwater change for other calculations? No. What it does is it's only doing it on that dissipation. So, if as you saw, if I go to a plot, if I slide it up and down, it's only doing it for that dissipation. But of course, if you think that's what it is, if it goes to a certain value, and you say, okay, like it's 8 kilopascals. So I could double check and say, okay, what does that relate to the groundwater table? And if it's different than what I put in, I can go back, change the groundwater table, and then when I open up the dissipation curve, so if I change this like to 3, if I go back to the dissipation curve, the first thing it says is, okay, we're going to recalculate, which it does. Now if I open, see, it's moved itself to the 3. So, it's clearly wrong. It should be up where I had it before. So it doesn't affect the other calculations. It's only if you change the groundwater table in the properties table that it does it. So where can you find the RK values for each soil type? RK, now I'm assuming you might be talking about this new kg value. Oh, right, yes. Okay, so it's related to bearing capacity. Yeah, right, okay. So there it is, this RK value. It's in the CPT guide, and basically it says that for sandy soils it's about 0.16, and for clays it's about 0.3. That's what theory says, that's what experience shows as well. And the program defaults to an average value of 2. So you can vary it. It's in the CPT guide, but basically it's about 0.16 if it's a sand, 0.3 if it's a clay. The program defaults to an average value of 0.2. But it's only for ultimate bearing capacity, and in most cases ultimate bearing capacity is not controlling design, so it's not that big an issue. It's just giving you an estimate as we had done, and then with that estimate you then go and do a settlement calculation. So it's often the settlement that controls, and the bearing capacity calculation is just to guide you on what's a reasonable allowable bearing pressure for your settlement calculation. Now it says, can I explain the 20% rule? Yes, I went through it rather quickly, and here it is here. And I think in the Eurocode there's a requirement that says you only need to do the settlement calculation down to a depth where the applied change in stress no longer exceeds 20% of the existing effective stress. That's essentially what it says. So if you think of the bulb of pressure, you only need to do the settlement calculation down to where that contour of the 20% change in stress would be. And it says you can pretty well ignore that below. But the program, you can toggle it on or off to see what the effective. And here you can see that right here the settlement. I'll take the creep settlement off. The primary settlement calculations about 2.5 centimeters, and if that's with the 20% rule removed, so it's 2.5. And of course, if I apply it, it went to 2. So it didn't make a lot of difference, but it does sort of extend the bulbar pressure further down. It depends on your project if you want to apply it or not. So conversion to accept L over B values in settlement with a decimal. That's a good question. I'm not sure about that. Settlement. No, well, it might do, yes. So you can type a value in, yeah, so you can. The answer is yes, it can. Yeah, there we go. So it does take a decimal. Is it elastic consolidation or total? It's end of primary consolidation. So it's consolidation settlement. But of course, in the sand layers, it's the same as the elastic settlement because consolidation is immediately. And so they're essentially one and the same. That's why we use one-dimensional constrained modulus. So it is a consolidation calculation, and it's end of primary. That's why we can add in a little bit of creep. But by using one-dimensional constrained modulus, it makes the calculation so much easier to go between sand layers and clay layers using just that single value. And so it depends on the soil type. Is it possible to assume a matrix suction profile above the groundwater? The answer is no. I don't think so. I mean, you know, if you put in a water table as we've done 2 meters down, it assumes the pore pressure is 0 above that. I don't think it would let you put in a tabular, like you can put in non-hydrostatic and put in tabular values. I'm not sure if it would allow me to put in a negative value. It probably would. I could type in a negative value. I won't do it here, but you can try that. So yes, maybe it can. If you think you have an estimate of it, you probably could put in a suction as a way of trying to get a better handle on what the effective stress is. Often the key is the cone is going to interpret the data based on what the stresses, the effective stresses in the ground are. Now, if they're suctions, you don't actually know what they are, but the cone is going to respond to the strength and stiffness of the soil at that effective stress. So if that's what the suction is going to be in the future, then you maybe don't care that you don't know what it is. Is there a way of export to GINT? Yes, there is. You can export as a graphic. I've forgotten exactly how you import to GINT, but I know people do it. I'm just not aware. Can the software estimate pre-consolidation pressure? Yes. I mean, it's estimating OCR. It doesn't actually give you pre-consolidation pressure. We toyed with flipping that plot to pre-consolidation pressure. For now, I tend to prefer OCR. Of course, you've got the vertical effective stress in the table above, so you can do the calculation. You can export it as a spreadsheet. You can take the OCR, the vertical effective stress, and of course, calculate the pre-consolidation pressure in the spreadsheet if you want to. So the very last question, I know we're running out of time, can you talk more about rigidity number and soil structure? And the answer is yes and no, but the last webinar talked about that. What you're talking about is this normalized rigidity index here. And that's what our last webinar was about. And so since we're running out of time, I really suggest that maybe go back and watch the previous webinar that talked about these updated charts. It explained what this rigidity index, this normalized rigidity index, KG, is. It's essentially the G over QT ratio normalized as a function of the normalized cone resistance, you know, because it varies with the state of the soil. So it's not a constant value. It actually varies, as you will see by the slope of that line. And so that was covered in the previous webinar. So I apologize again that we had a little bit of a slow start. I had a problem with my computer opening up the webinar software, but hopefully it all went well enough. Hopefully I covered the ground. You can see that CPeTIT is a very powerful program. Version 2, it just gets more powerful. And as I remind people, for 249 euros or under 300 US dollars, it's a remarkably cost-effective and powerful tool. And there's a reminder, Gregg and myself, we helped write and sponsor it, but John Ioannidis of Geologismiki wrote the program. Gregg and myself don't get anything in return. We agreed to work with John because we wanted to see software like this available. So although I promote it, I'm not promoting it because I get a cut of the sales. I do not. I promote it because I want to see people use the CPT more, and this is a very powerful tool that makes it easier for you to do that. So I encourage people to download it. You go onto the Geologismiki website, download it. You can download a free 30-day trial. It does everything except it won't print for you. And as I say, it's only 249 euros. And if you bundle it with Slick and Section Maker, which is a simple 2D cross-section software, it's a very, very cost-effective package. And as you can see, a very powerful tool that helps you interrogate the data and interpret it to be quite valuable. So hopefully that's been of value, and we're going to do another webinar, and the next one will be on Slick. So it'll be a bit like this, a worked example using the liquefaction software. So hopefully you'll come back and join us for the next one. This will be recorded and it'll be available on the website. Thanks again, and hopefully you enjoyed it. Bye.